Welcome everybody, thank you for introduction. So this is a collaboration between Tuomo Nissinen, Aste Gaster, Ralf Hietscher and myself, which has started with the implementation of parent grain reconstruction in MTEX. And now with those new possibilities, we've extended the capability to also look at habit plane determination from 2D orientation maps. And new features have been shipped with MTEX 5.9, which now realize this kind of functionality. So for the people who don't really know what a habit plane is, I think time for mentioning martensite and habit plane or in your talk, so there's a natural flow to what we're talking about. So imagine you have some kind of a crystal structure, so some material which is consisting of one phase, and you apply some deformation or some cooling to that material and you induce a phase transformation. That means the original phase, which is the parent phase, forms a new phase, which we here call the child phase. And of course, when a new phase forms, we must have some kind of interface between this original parent phase and this new phase. And atomistically, usually this interface is such that we can kind of, let's say, get a very smooth transition energetically at the atomistic interface. So it's usually kind of perfect interface if we look into a very high resolution microscope. And in this example, we have a 111 plane in the parent phase parallel to a 110 plane in the child phase. But what happens when we have a phase transformation that we often have some constraints, for example, mechanical constraints, when we have some shear or volume change involved. And what then happens is that we kind of need to accommodate this deformation. And what the result of this is that we then get some kind of latch interface. And of course, when we then zoom out of our atomistic picture here, we can then only identify this kind of plane as the interface. And the habit plane is exactly that. It's the macroscopically observable interfacial plane between a parent and a child phase. So just to show it again, if we have one grain of a parent phase and we form a child phase, then this one is the habit plane, even though maybe atomistically the interface looks different. And that's what we're trying to identify with our algorithm. So habit plane deformation has a very big background in martensite research. This year's, for example, work from the 80s, but even way before that, people started trying to characterize the habit plane. In martensite and steel, where it's a quite big topic, we have an atomistic interface of the 111 plane in austenite, parent phase, with the 011 plane in martensite, which is the child phase. But we can also see that macroscopically, this plane actually shifts to more of a 575 plane in austenite. So we can see that the habit plane is not really corresponding to the atomic kind of interface. And if we can identify this kind of habit plane, we have some way of actually characterizing the rapid phase transformation, because people of you who know martensite formation, it happens almost instantly, and we cannot really observe much about how it's going on, but the habit plane is one very big piece of evidence of what kind of phase transformation happened, what the mechanism was. So there's been a lot of interest in characterizing this habit plane. And it also is needed to provide validation for some models that try to predict or model martensite formation. So how can we determine the habit plane? Traditionally, this has been done most recently, I would say, with transmission electron microscopy. There have also been some previous attempts with other techniques. In transmission electron microscopy, we can take quite high resolution images of a microstructure through an electron transparent foil. And we can either look at individual layers of martensites. We need individual layers of martensites that are embedded in like an austenite matrix, so that we have both of the orientations. And then we can either tilt the sample so we actually look down the habit plane, so that's called on edge kind of orientation, or we can do something called single surface trace analysis, which I will demonstrate later. Of course, we have the big advantage of great spatial resolution, so we can measure angles and stuff very nicely. The problem is, though, that this is a very time-consuming procedure. We have a limited range of suitable alloys because we kind of need to have a composition where both phases are stable and present at the same time. And we also have quite poor statistics because we can only sample a very small volume of material with this method. So to show a little bit how a single surface trace analysis with transmission electron microscopy works, I have prepared this. So if we have a single surface trace that we identified, here the blue arrow, we know that this trace is lying on the habit plane. So there's basically a big ring of possible potential habit planes where this trace direction could be associated with. And the trace is going to be normal to all those potential habit planes, but we don't really know what is the actual habit plane right now. So what we can do is to just identify a lot of those traces, ideally in different parent grains. And if we then have a lot of, let's say, potential habit planes and we can find a crossing point, then we know, okay, this must be our habit plane. And that's usually what's done with this kind of conventional method of doing this. So there's a lot of measurement involved and a lot of tedious work, and the accuracy is like average. I mean, you both do austenite and math-size orientation as well. So it's quite limited what we can do here. So our thought was, okay, orientation maps is something we know. Can we not get a habit plane from orientation maps? This is a quite big orientation map of Bluff mountainside, which our collaborator Tuomo has acquired for us. And traditionally, those orientation maps are associated with low angular and spatial resolution. They're also prone to distortions because it needs quite a long time to acquire. Of course, the question is here, can this really be accurate enough to determine the habit plane? And the word is out, no, cannot be done. But we thought, of course, we have excellent statistics. So maybe that can actually help us in getting a good fit to the habit plane. And that's what we try to do in this project. Here, for example, we're looking at 1 square millimeter of area with 4 million pixels. So if you think about it, it's 4 million individual orientation measurements, which is quite mind-blowing. And we can then apply the parent grain reconstruction to also have the associated parent orientation with each of these pixels. So we have tons of data we're sitting on, and we just have to figure out, okay, can we use this for something? And of course, the key tricky point is, of course, to determine the traces in this material, because once we have the traces, we have the orientations, we can probably figure this out. So how to determine the traces? There are different methods we've been thinking about, and there are probably more than what I'm going to be presenting today. We can maybe first start with pixel-based approaches, and one of them is fast Fourier transform-based. I'd like to mention to Timon, maybe some of this can also be inspiration for you for identifying slip systems. I'm not sure, but maybe. Because basically we're also looking at finding some kind of directionality in our microstructure. So this is one prior austenite grain, so one parent grain, and we have 24 different magnetotic variants possibly in this grain, and we try to highlight them individually. So this is one magnetotic variant, and the orange one is also a magnetotic variant. We can see that there's some kind of directionality to the microstructure, and that actually reflects the habit plane, which is parallel to the long edge of these kind of grains. So if we now actually only look at the blue intensity and only look at the red intensity, we can take the Fourier transform of this, and what we get is actually some kind of frequency distribution, which looks like this. We can see that there's some kind of elliptic intensity in here, and that simply has to do with the fact that if we look into this direction, we actually have some kind of intensity on, intensity off kind of periodic signal. Whereas if we look along the habit plane, we actually only have no intensity or full intensity. So actually this kind of periodicity of the structure is reflected in the Fourier spectrum, and then by somehow, let's say, fitting an ellipse to this and then taking the short axis, we can get the trace directions of this microstructure. Another way, which is a little bit more maybe difficult to explain, but it works quite well actually, is the radon transform. So we start this with the same kind of initial situation where we have pixel-based data of the different variants. And then we take the radon transform of this. And the radon transform, if you don't know, is basically just a line that we rotate by 180 degrees. But each of these points, so the points are the shifts. And then we basically see, okay, how much intensity do we integrate along this line? What we can see is that we have one region here where we have a lot of high intensity and low intensity. And that is, again, if we have a line that's kind of oriented in this angle and we go through our map here, we kind of might hit a big chunk of material, no material, material, no material. Whereas perpendicular to this, we have quite a smeared kind of region. So actually also the periodicity of this microstructure is also reflected in this radon transform. To process this further, we can take then the FFT along the shift. So in 1D, and then basically we get some, it's not so visible maybe for you, but we get some higher frequencies around here, in which if we sum up the frequencies, we actually get a peak here, which is associated with the direction of the last. And this way we can also determine the trace using the radon transform. Then there's two more methods that are based on grain boundary segments. So here we start actually with computing the grains first in MTEC. And then we look at the boundaries of those grains. One method, for example, looks at a circular histogram. So basically, what is the overall length of grain boundary is along a certain angle. And of course, parallel to those elongated grains, we have more grain boundary, and this is reflected in the circular histogram. So here we can also determine the long axis of these distributions to then get the traces. And a very similar approach is the characteristic shape approach, where we actually sort all the grain boundary segments according to the angle and kind of concatenate them. And this way we get those elliptic looking shapes. And here as well, if we just take the long axis of that, we get the trace. So there's plenty of ways to get the trace. There's probably more than I've been presenting, but at least it's possible. And once we have the trace, how do we then get the habit plane? So here is an artificial data set of traces that have been kind of modeled or measured in a microstructure in the specimen fixed reference frame. And the colors here, they represent different prior austenite grain orientations. So different prior austenite grains or parent grains, we have measured those traces. And they're all sitting on one ring right now because this is the imaging plane and they have some kind of XY orientation. So the first thing we could do is to rotate these into the parent reference frame, of course. So we apply the parent orientation for all these traces. What we then see is that this imaging plane, which is a big circle, then gets projected into the parent reference frame. So we have those semicircles or arches in here. And of course, if we look at this, we don't really see a habit plane yet, right? And the problem is here that we're not really looking at the symmetry operations that are involved in the phase transformation, because this is basically just a parent reference frame, but we measure the traces of the magnetic phase. And from each parent grain, we can form up to 24 different variants of this magnetic phase. And we need to take into account which one of these we've actually been forming. So what we need to do is we need to apply the crystal symmetries of the newly formed child phase, the magnetic phase, to this to actually get to the habit planes. And if we do this, then we get this huge jungle of points. So now we've basically multiplied the number of points that we have by 24. And we can actually see that there are some kind of maybe planes present in here. But the point is that we now look at all equivalent habit planes. But if we actually can figure out for each measurement point which variant are we looking at and only take that specific symmetry operator for a certain variant, we then can actually get to a place where these are the traces, and we can find a point that's perfectly or like best fit perpendicular to those traces, which then is the habit plane. Yeah. So the trick here is really to know the specific symmetry operators or to know the certain variant of your magnetic microstructure, and we get this from the prior austenite grain or grain reconstruction, and this way we can then actually fit the habit plane. So the big question is now, what if we don't get the traces right? Because Word says that EBSD, Word has that EBSD is not very accurate, so we tried to actually test this with also an artificial data set. So we had this data set where we knew the habit plane and we extracted some traces from that. So we had perfect traces, perfect habit planes, and then we applied some distribution to those traces to figure out, okay, what if we actually are not that good in identifying our traces? So the blue distribution shows a situation where we just have some standard deviation around a zero mean. So it basically means this is the perfect trace, and then we have some kind of deviation. And we see that there's maybe an average angular misfit of 7.6 degrees from the traces to the real habit plane, but the habit plane we can fit from this, whereas the real habit plane only has an offset, or sorry, a deviation of 0.3 degrees. So we actually get quite close to the real habit plane, even though we impose this kind of big variance in our trace direction. And even if we apply a shift of, so like a systematic kind of deviation of 10 degrees, we still actually only get 0.4 degrees in deviation from the real habit plane. And I was initially a little bit surprised by this, but of course, if we look at a lot of different parent grains and we have those symmetry operators of all the different magnetic variants, kind of the systematic shift that we apply here becomes randomized, and it actually just results in a higher variance of the signal, but we still actually get a quite spot on habit plane. So that means if we have some kind of distortion in our microstructure, or not that good at actually fitting the habit plane to the microstructure, it doesn't mean that much. It's actually, we can see that the error is quite low from that. But what about errors from parent grain reconstruction? Because remember, we need those symmetry operators to rotate everything in place. And if our parent grain reconstruction does not do a good job, then we might identify the wrong symmetry operators, right? We also tested this with artificial data. Here, for example, we assumed that a third of the parent orientations that we reconstructed were falsely reconstructed as their twin orientation. What happens then is that we get a second suggested habit plane, which is not the actual habit plane, and they have an intersection point at 110 here. What if we, for example, look at an orientation relationship which is not very representative of our microstructure? Then we also have problems with misannexation. We get several different solutions for the habit plane as well. But still, if we then look at the actual effect, the last example here is a combination of this distribution and this kind of a poor orientation relationship. Still, if we fit things, we're only off by 2.8 degrees. So it seems to be quite robust, but all in all, a good parent reconstruction, grain reconstruction is quite important to make this a solid procedure. So we wanted to validate our algorithm on synthetic microstructures. And we did this, so we actually had a microstructure where we knew exactly, okay, this is the habit plane, because if you have experimental data, we don't know this in beforehand. We took a 2D section from this, and here you can see that we have an FCC phase, which just transformed to a BCC phase. And the blue lines here are actually the traces that have been identified using the radon method. And then we can see how our 4 different kind of trace determination algorithms perform. The 255 is the actual habit plane, and all of them are actually spot on, apart from the Fourier transform, which has a slight deviation, but is still within the right ballpark. So it seems that the method works. And therefore, we then applied it to real data. So we acquired some EVSD data sets of martensitic steels with different parent grain size and carbon contents to kind of have some variation and hopefully see different habit planes as well. Here we see the martensitic variants with prior austenite grain boundaries around them. And here we have the reconstructed microstructure. And this is the low grain size. And here we have a large grain size, just as an example. So what we get then is this distribution of traces, which again nicely follows some kind of plane. And if we then take the ODF from this and find the best orthogonal direction, we get this habit plane normal vector. You might see that we have a pole here. I will go into this later. And if we do this for all the data sets, we can see how they distribute. So they're all kind of in the 111 austenite kind of corner here. And if we then magnify this, we can see that in the 0.35 carbon case, we have both methods, the radon method and the characteristic shape method, giving quite consistent results. And there's a slight difference between the 2 different grain sizes we have applied. And then for the 0.7 degree carbon, 0.7 weight % carbon steel, we also get quite consistent results, closer to 557, which fits quite well with literature data. The only thing we were not so happy with is the deviation here between radon and shape for one of the conditions, which probably has to do with that we have 2 different types of martensite present in the material. But you can read about that in the manuscript if you're interested. So the last one I want to maybe highlight is this pole that we've been looking at here. So you always see this kind of pole at -101 consistently in all our measurements. And we'll, of course, a little bit ask ourselves, what is this pole about? So there are possible reasons. We're not really sure yet what it is. So it might be that we have a true and a false habit plane that are crossing. You might remember from earlier that if we have a parent grain where we falsely identified as the twin direction, that we actually get a crossing point right here. So this might be an artifact from an imperfect parent grain reconstruction. So basically falsely identified twins. There might be other misindexations involved, but there's also a possibility that this is a real variation in the habit plane that we observe. And personally, I think that's more likely. Because the long axis of all the lavs of martensite that we observe is -101. And I think if we have a microstructure where those lavs are, let's say, oriented in 3D, we take a 2D section, there's just a higher probability that we observe those lavs with the -101 trace. So from my point of view, it's maybe more likely kind of probability distribution of imaging a certain direction, trace direction. Or it could be a combination of both effects. So we're still looking into this. To conclude the talk, habit planes can be determined from EVSD maps, regardless of the involved crystal structures and the transform fraction, which is a novelty. We have good statistics, and confident parent grain reconstruction are key for this. The accuracy of trace determination has a minor effect on the habit plane, which was a little bit surprising to us. The method has been validated with synthetic data and synthetic microstructures. And we also applied it to martensitic steels, which shows excellent agreement with literature data. So all new functionalities are shipped with MTEX 5.9, and we're also going to be posting some examples in MTEX and also new OR tools library soon.